Hi, this is Theo, your quantum group professor. So we'll have today the first lecture from the series called Tannakian duality and then diagrams and easiness. So that's going to be actually the most technical lecture from all six. So we already had operator algebras and then quantum groups, representation theory. Representation theory was already technical, some tricks there of analysis due to Voronovich. Now we'll get into some really tough algebra, Tannakian categories. That's among the toughest algebraic things in this world. And then at the end, well, why we're doing this for applications. So at the end, we'll have some true applications, tough analysis. We'll compute the measures of the main characters for these quantum groups we're talking about, ON, and you'll see under three versions. We'll get some very interesting measures from probability. I mean, Gaussian laws and then things coming from random matrices from Wigner, Voiculescu, and goes to infinity. So it's going to be, yeah, something quite special today. Very tough algebra to start with and tough analysis to end. Okay, we'll see. Hope we'll survive all this. Let's find this presentation first. Here we go. So, yeah, I was telling you the Tannakian duality diagrams and easiness. That's the plan for today. Okay, that's how we started. So as the plan, we'll talk first about tensor categories in general, definitions, all that. Then we'll prove Tannakian duality after formulating it, so that's going to be quite tough. And then at the end, as an application, we'll get into these three quantum groups that we're talking about, especially ON plus, UN plus, we want to understand them. And first we'll build on Tannakian duality a theory called easiness, which is somehow the case we're interested in, the most important, with a lot of combinatorics there. It will be just the beginning, okay? Easiness will come back in the next lectures more in detail. And with this, we'll find some applications to the three quantum groups. Yeah, especially this analysis business. Why analysis and not other things? There are so many things that you can do once you have Tannakian duality. Because, well, as I told you the last time, finding all this Peter Weibel, that's the main application was Kesten amenability, suggesting computing the law of the main character. So that's what we'll do. I mean, that's the main computation, the law of the main character. Everything else like fusion rules, other stuff is a bit secondary. So that's why we'll get into this. And of course, the end will be, of course, a bit short. So in the next two lectures, number 5 and 6, we'll go to that more in detail. To be more precise, we'll see that quantum permutation somehow is missing to be done next, and more easiness, and then more analysis and other things. Okay, so in order to get started now, oops, no, once again, yeah, we already had these slides for people maybe who didn't attend the last lecture. So what's the idea? Compact quantum groups are interested in that. So these are given by Voronovich algebras. These are the axioms, extremely simple algebra with binary matrix, such that you have delta epsilon s. Important remark: S square is the identity. That's something that we really love. Then basic example of such a co-representation. Oops. These are not the axioms. This is the definition of a co-representation. It's just so similar. So, okay, let's not keep it like this, not reshoot the video. Actually, it's a good thing that I missed this. So, yeah, the definition of a co-representation is more or less the definition of Voronovich algebra. What changed is that well, you have the small n instead of capital N. I mean, it's not the same thing as U. Now, as basic example, you have the fundamental co-representation. And yeah, that's what I was saying. The axiom state precisely that you must be a faithful co-representation. Faithful meaning that the coefficients generate A. Now, in the classical case, what we have are the representations of G, and to be more precise, the finite dimensional unitary smooth ones. So we'll always omit these three words: finite dimensional unitary smooth. Everything will be like that. And then we have Peter-Weil theory, and yeah, there are many results there. The main one is that if you take the irreducibles, their coefficients somehow sit inside this smooth algebra A in a direct sum position as a coalgebra. Okay, it's not an algebra isomorphism, it's a coalgebra, and they are orthogonal, these components, with respect to the Haar functional. Okay, now let's go to work. So what's the idea? Well, it's a bit hard to explain why to get into all these things, but believe me, that's important to the Tannakian duality. So let's start with this. Yeah, maybe. And the Tannakian category of Voronowicz algebra is just the collection of these home spaces. KL being now, of course, colored integers because U doesn't commute with U bar. So the rule is that U to the white is U, U to the black is U bar, and then multiplicativity. For instance, you see this K here, U to the power K will mean U tensor U bar, tensor U bar, tensor U, tensor other things. So see, it's really words on two things, what we call black and white. While looking at these beasts, well, because they well, I say it's related to Keston amenability. Okay, that was the conclusion from last time. Looking into Keston amenability, and the moments of the main character are the dimensions of these guys. Okay, so yeah, very good reason. There are many other reasons for looking at these spaces. So for the moment, I don't have, it doesn't even look like a category. It's some spaces which are naturally there, and you want to compute them. For instance, their dimension gives you this Keston things, random walks. Now, well, the point is that this form a tensor category, so that's going to be our starting point for what we do today. These spaces that we want to compute, definitely, actually they form a tensor category in the sense that if you compose, of course, it's stable under composition, and you can also tensor intertwiners, you get intertwiners, also apply stars, so that's something that we know for long from lecture 2. And the other remark is that it's not an abstract tensor category because these home spaces are intertwiners. They live on some Hilbert spaces, to be more precisely on powers of Cn. So if you want, C is a subcategory of the tensor category formed by linear maps between tensor powers of Cn. Once again, we have a convention here for color integers. So if you want to raise h to the k or to the l, well, h to the white is h itself, h to the black is h bar, and then multiplicativity. Of course, h bar is h too. I mean, it's Cn, but sometimes you need to use this for spaces which are just finite dimensional Hilbert space. So even if you don't, when you don't know that it's Cn, it doesn't have a basis. And in that case, you really need colored integers because you have both h and h bar, which of course are isomorphic once you choose a base. So there's a subtlety here. Okay, so we have, once again, what's the point? So we want to compute spaces definitely for a number of reasons, including this Keston business. And now our remark is that this is a category, very good, and also it's a category of this category here of Hilbert spaces. So we have a bit of structure there. Now we want to reconstruct our claim. That's the claim of Tannakian duality, is that A can be reconstructed from these spaces. So this is not trivial. So let's start with the useful preliminary result, which is very nice, and you will use all the time this lemma. So given a morphism, which must be surjective, I mean, by morphism I mean here coordinates go to coordinates. So it's surjective, it's a quotient map. This must, of course, increase the home spaces, right? If you take the quotient, home spaces increase. And now the theorem says that if all these inclusions are equalities, then your morphism, your quotient map is an isomorphism. So this is very useful. It's really a criterion for isomorphism, and we'll use this several times actually during this presentation. So why is this true? By fit or while. So contradiction, let's assume that pi is not an isomorphism. So now if you look at Peter Weil, this decomposition to direct sum, you certainly some irreducibles here will become reducible here. So the home spaces will increase because any irreducible is inside such a Peter Weil representation, UK. So the corresponding if you want and UK will increase from some K. So that's your proof. Now, in connection or reconstruction problem, it's solved for quotients, okay? So as long as you have a quotient, you're in a quotient situation, your category describes the quantum group. Now, of course, we want to do it without any quotients. We want to prove that for any A and B, arbitrary, not related by a quotient operation, if the categories are different, then A, B are different. So that's the thing to be done. And well, this was very simple in 2-line. When A, B, you have a quotient map. If you don't have that quotient map, it's gonna be, I don't know how many, 20 slides. So it's considerably more complicated. Now, what's the starting point for reconstructing? So we know nothing. I mean, an arbitrary Voronovich algebra, what do we know about U? So it's all about U, right? U, the fundamental co-representation. We only know that it's biunitary. So this will be a starting point, obviously. That's all we know. So let's translate the biunitarity condition categorical terms. And the translation is precisely this. So if you take the operator, which it's a vector somehow, but you view it as an operator. So you take this vector, sum of I tensor I, the basic vector in tensor product, and R is by definition the operator which maps 1 to this vector, okay? Why this? Because we also want to talk about R star, okay? If you just take a vector, it won't make sense to take the star of a vector. That's why you have to use this R, an operator. And now the thing is that the matrix is biunitary. What does it mean? So U unitary is 2 conditions, right? U star equal X, U star U is 1. So when you have 2 equalities, and biunitary means that the transpose must be unitary too, so 2 more. So it's a collection of 4 equalities. Well, these 4 equalities are exactly equivalent to these 4 conditions here. Where, of course, so what do I mean by home? I mean, these are taken in a formal sense, okay? So we know what home means for co-representations, but that just means if you remind the definition of home of 2 things, you can put any matrices there. I mean, there's absolutely no problem. It makes sense. It's the operators which intertwine them. So, okay, you see, that's what is meant by this theorem. An abstract matrix of an abstract C-star algebra is biunitary if and only if these 4 relations hold in a formal sense. Now, so the proof, as I told you, have 4 biunitarity relation. If you look at them, these are exactly these 4 relations. So with this, we are ready now to formulate a bit what we had. So for the moment, we know that this Tannakian category, yeah, it's a tensor category, and it's a subcategory of the Hilbert spaces. But now we have this R operator coming into business, so we must include it in our axioms. So here are now the complete axioms for the tensor categories, those that we will use. So we take a finite dimensional Hilbert space, that's here but without basis, not necessarily. A tensor category over H is a collection of subspaces like this, which satisfies, so it's a category, tensor star category. The first 3 axioms, or other 4 identities, are needed too. Plus this thing that we just found, that R, you see, is contained home U tensor U bar tensor U. U tensor U bar means white black according to our conditions, and there it's black white. So this is it. So just basically what we're doing here is the observations from the beginning that it's a tensor category, these spaces, and also it's inside the Hilbert thing, and it contains this R map. Our claim now is that this is exactly what we need. I mean, such a category produces a Voronov algebra and vice versa. So first of all, yeah, the vice versa, we already know it. So take a Voronov algebra, then a Tannakian category, the home space is form a tensor category here. That's what I told you. 1, 4, we knew. 5, this RC, we already did it. Now let's go in the other sense. So given a tensor category, can we construct a Voronov algebra? And the idea here is very simple, of course. You have to take C of UN plus, that's the biggest thing, UN plus, and then mod out by some relations. Well, you just put the relations coming from the category, okay? For any KL indices and T in CKL, T must actually be an intertwiner, okay? There's no thinking. I mean, it can only be this, right? So good, we have a construction now, and let's what we have to do. Well, first we have to prove that it's a Voronov algebra. So this follows because anytime you add such a relation, delta epsilon is factorized. In other words, the ideal is a Hopf ideal there. There's a short computation there to be done. These kind of relations are of Hopf type. So you have just compute and you get your factorization. Now, let's study also this construction. So we have now Voronov algebra categories have arrows in both senses. We want to prove that it's an isomorphism, and the two compositions actually want to prove that there are identities, and one of them is trivial. So what's trivial is the following thing. So in case where C comes already for a Voronov algebra, what you get, well, you actually have a quotient map. Yeah, it's not trivial. Sorry for that. You have a quotient map from AC to A. So why is this true? So in order to construct a quotient map, you must prove that all the relations here which define AC hold in A. But they do hold, I mean, because NET is an intertwiner. So it's trivial, okay? So summary now what we have. We have axioms for A, Voronov algebra, size n always. Axioms for C, that's this tensor category business we're talking about. So with the R operator included at the ends. We have a correspondence in one sense. So from A to C, you just, the category is just the home spaces. And in the other sense, that this is exactly what was written on the previous slides. So let's take a look at that. Take C1 plus, and then you assume that NET intertwines. And that's what's written here, you see. So C is your input, and you assume that it's included here. I mean that it really intertwines any guy in C. So it's exactly this, shorthand. So you see, well, 4, I mean, uses notation from 3. So that's why it became very short. So I have everything. I mean, we have objects here, A, objects here, C, well defined, correspondence. I want to prove that these are inverse to each other. So very good. At least we have a problem now to be solved. Now, let's go into, there are a number of steps now. So this is a kind of algebraic problem, which, well, you do it by steps. Each step is trivial, and if there are enough steps, you're done. That's always the idea in algebra. And so I don't remember here. There are 6 steps and 4 more. So anyway, so maybe as a comment, we get into all this. Yeah, it's really this kind of algebraic geometry thinking, and actually these things come. There is a long story here, so that's one proof that I'll present today. There are several of them. So all this in tensor categories comes from Grothendieck. So a student of him, Saavedra, looked at this in the 60s or 70s. He wrote a small lecture, yellow lecture notes, and then many other people got inside, like Delin, Lopliker, Roberts, many others, and then Voronov. So this proof here is a recent proof due to a student of Meshbeev, Sarah Malakarn, which is, well, Well, on paper, Sarah's paper is like 4 pages, but for those who know, for those who don't know, you'll see, I mean, it's a bit technical finally. And there are other proofs. So that's one proof. The other proof is the one in Voronovich's paper, Tanaka duality, which is kind of straightforward, but is different from what we're doing here a bit. You see here, you only work with Peter Weil representations. Voronovich works with all of them. And in a certain sense, it's simpler, but also the definitions get bigger. I mean, yeah, hard to choose between the two. And yeah, as a remark to Voronovich, if you read that paper, definitely you have to read it. So if you get into this Tannakian business, you have to be aware of what's going on. So that's one proof. Then Voronovich, but with the square is the identity that simplifies a few things in his paper. And then also what you have to read is duplicate Roberts and Deligne. So these are, in the classical case, you don't need this notion of Tannakianity. I mean, the category can be abstract. It still produces a group, even without embedding into a Hilbert space. It's very, very interesting business. And the quantum analog of these are not really known. And then what else do you have to read? Ettingovnik, C. Ostrick, in the finite case somehow, and that one is finite. That's an amazing paper that they wrote. So yeah, again, so many things to be read. So Saavedra for the story, the yellow lecture notes, the Duplicate Roberts, Voronovich, and the NO paper, and then Malakarn. So what we'll be doing here will be in the paper of Malakarn explained. Okay, let's go now. So what was the, yeah, we have the statement. Okay, let's prove it now. We'll do these steps. I don't know, Grothendieck. Yeah, try to be trivial every time. So consider the following category. So we want to prove this. I mean, we have C goes to A, goes to C. So we want to prove that these things are true, right? The two compositions are here. And the point is that, yeah, contrary to what I said before, it was a mistake there. It's not that one is trivial, but one implies the other, okay? And that's what we have here. So it's enough to prove one of them. And also in one of them, which is the first one of the inclusions is automatic. So you see, normally you have 4 inclusions to be proved, 2 equalities for 2 compositions, so total of 4 inclusions, and this says that only 1 inclusion remains to be proved. Very good. Why is this true? So first of all, but by what we said here, AC goes to A. We always have an arrow. So ACA goes to A, we have an arrow. On the other hand, so we want to prove that one implies to, assuming that this is true, you have CA is CACA. So these things are independent, but if you compare them, this means that these are exactly the categories here, okay, for the algebras here. So in the situation where we have a quotient map and the categories coincide, and that's something that we've seen in the beginning, that nice useful result that in this case must have isomorphism. So that KC is A, that's what we want. Finally, C included into CAC is the same thing as this. I mean, it's just clear. Very good. So we have just one inclusion to be proved, namely C includes CAC. Now, in order to do this, the idea will be first. Well, it depends on C, the category. It's a bit annoying because if we want to do algebra, we need algebras, right? Here we have a category. So let's make an algebra of this out of this category. And here we go. So we just take the sum of these spaces which belong to this, which are operators, right? It's a Tannakian, and which belong, if you want, to this big sum. So this will give us a star algebra. Okay, it's not closed. But in order to get these star algebras and use our knowledge there, a bit of spectral theory, we'll truncate at NES. So S is the length of the, with bars, I denote there the length of the color integer. I remind you, these are colored integers all the time. So this is the length, it's a usual integer. So also truncate at S, and you get, of course, a star subalgebra, which actually is star algebra because it's finite dimensional. So no topology there. So very good, that's our idea now. So we converted categories into algebras. Very good, we can do algebra. And even better, these algebras, we truncated them. It's an SC star algebras. So we can do sister algebras, okay? Now comes step 3. We have finite dimensional sister algebras, and something which is that we need to know about them is the von Neumann-Bicommutant theorem. Well, in this very simple setting, finite dimensional. So for any sister algebra of the matrices, it's equal to its bicommutant. So is this true? This is something that we already know because B can be decomposed as a direct sum of matrix algebras, right? That's something that we learned in lecture 1 and heavily used for Peter Weil when you decompose these representations. That's what you use. Now let's look at the commutants. In this picture, it's clear. I mean, the commutant of each matrix algebra is C, so you get just C's, and now if you take the commutant back, the C's become matrices again. So you get B itself, very nice. Of course, as a remark, this is actually true for any von Neumann algebra, but that's another story. Recommended read, okay? Von Neumann bicommutant, that's something that you might need in other situations, very important. So I'll use this trick now. So let's go back. We wanted to prove this, right? Remember, where actually one inclusion is trivial. That's the thing to be proved, okay? That's the identity if you want to apply to C. And that's my double composition. That I want to prove is the identity. So I want to prove this now. Well, that's the same as proving as the associated algebras, right? With this complicated, with this sum are the same, of course. Now, this is the same as truncating at NES. And now I can take the commutant if I want, okay? Because we have the bicommutant. The commutant remembers the algebra. So this is proved, they are equivalent. And in addition, so we already know that one inclusion is trivial. So this one too is trivial. This one too, and we take the commutant, it goes in the other sense, the inclusion. So very good. So finally, we are led into this fourth question. That's the one that will solve. So once again, it's becoming complicated. So I take the category. You construct this algebra by summing everything. You truncate in order to get your sister algebra, and you apply your commutant because the problem becomes simpler from the commutants. Okay, that's the idea. So prove that these things are equal. Now let's compute these commutants, okay? So at left we have something abstract, depending on C, we don't know, but at right, when you put your A here is the Voronovich algebra. So let's try to compute this commutant for a Voronovich algebra. And well, first we must compute this E thing, I mean the sum of all guys. Of course, you get the n space of UK. That's not a problem, it's by definition. Now let's compute the commutant, and the commutant, we use this very simple lemma. That's why the commutants come to play, because the guys who did it, like Malakarn and especially these guys, they perfectly know this, that it's easier with commutants. So for any co-representation of any Voronovich algebras, okay, it's very general. This thing here, which produces the coefficients, is a representation of A star, having as image exactly the commutant of n. So okay, if you think at it, yeah, that's why. So whenever you see something with representations, it's good to take the commutant because NV prime is something that you perfectly understand. It's the image of this representation of A star. So let's see how the proof goes. Well, A star is an algebra, right, with a convolution. So that's your convolution here. And coefficients is this, so it's done. Very simple. So that's a representation. Now this is by double inclusion. Okay. So time for a summary. So we want to prove Tannakian duality, right? Past a few trivialities, which means that 3 of the inclusions are either, well, they are implied by the first one. You just want to prove this inclusion. Now, by using this linearization construction and truncation and bicommutants of 3 things in a row, it's the same as proving this thing, which might look complicated, but which is not complicated because at least at right, this is just the image of this coefficient thing for this big representation summing all the Peter Weil representations up to level S. Very good. So now what's next? Well, we have to take care a bit about the left term now. So this is abstract, right? So somehow the idea, well, this one too is abstract, right? Because A, this is very good, but A comes from C, so you must have some control on it. So the idea somehow will be to model things. So we're done somehow with abstract algebra. We cannot get beyond them. We have to go now into some matrix theory. We'll do things there. So modeling questions. So we have to model AC in order to prove these things. And how to model AC? Well, AC is the algebra associated to a category. So it's basically, we're saying you take C of UN plus free algebra generated by entities of a biunitary, you mod out by all these relations. Now, the biunitarity condition actually comes from the Tannakian category because it comes from R and R star. Remember that, okay? That was one of their first lemmas. The fact that a matrix is biunitary is encoded by the fact that R is in the category, okay? We had these four relations involving R and R star. So finally, we don't need C of n plus. We can just take the free star algebra generated by square variables and mod out by all these things coming from C, the Tannakian relations, and you get our AC. And this is very nice because, so we got rid of UN plus in this way. This is very nice because the star algebra generated by square variables, something extremely simple. We have a model. It's this, these guys here. It's as dumb as that. So actually, we'll take both F and the dual because we'll need later the dual when doing all these computers, all that. We have some duals. So let's just take this very dumb algebra. That's a model for the star B algebra, if you want, on n squared generators. So why this? Okay, so F star, I'm very interested in F star for some technical reasons. Better to do it like this, believe me. So first, on this, yeah, it's a star algebra. So multiplication, just multiply the tensors, okay? And the involution is the involution. Now, we have delta and epsilon given by the usual formulas, right? So we have tensors here, right? You can play with them the usual way. So that's your co-representation if you want and co-unit. And now, well, this is the free algebra, right? Very good. Now we have to mod out by that ideal that I was telling you. Of course, we'll work with the smooth part because with them, yeah, for the moment we don't bother about complexions. So, well, you have to write down. I mean, in this model with tensors, see what these conditions T in home, UKUL mean. And you don't, UKUL, you see, you don't have them anymore. You have these standard generators of BFH. The matrix is okay. So in matrix terms, this T in home UKUL becomes this. Where is the same formula as before, just write the indices in a different way. Very good. So we know as the ideal producing AC. Now, here comes something more interesting. So the space itself is given by this formula, which appears somehow, which appears diagonally. That's very important. So AC star, right? It has a representation there, and appears just diagonally. Okay, there's nothing of diagonal given by this this kind of commutation relation, if you want. That's again an elementary computation. Now with this, so let's go back. Yeah, this will be our final results coming from modeling. So that's what we'll need for proving Tanaka. So let's truncate. I remember we started these spaces here and here, but now we need to truncate at level S for proving our thing. Where was it? Yeah, we want to prove this at level S. So now let's truncate these spaces, these big model spaces, and we have well, this. That's the main thing. The AC star is exactly the commutant of EC. And the image we're interested in is the truncation at level S of this thing. So all this follows from this interpretation of AC star. So finally, we're ready to prove our results. So we have Tannakian correspondence given by this thing here. I mean, you just take the tensor category in one sense. In the other sense, by assuming that the category is really for inside the intertwiners. So how to prove this? Well, I remind you. So there were two parts here. Okay, three parts here. Well, the first parts were preliminary with categories, all that formulated Tannakian duality. The second part was with the truncation, concomitant, all that algebra, and the third part was with the modeling. So at the end of the second part, we concluded that we want to prove these things. Okay, so it's exactly what we want to prove, but linearized in terms of these things and truncated others. So that's what we want to prove now. Now, there are some point of competence. So that's on these computations here that we did finally about the dual. So let's take the dual now. So that's the same as proving that the forms vanishing here are the same as the forms vanishing here, right? Very basic functional analysis thing. So we use now the fact that we know what's the dual of AC. So from before, I remind you that AC was modeled inside of stars. So it's a star divided by a certain ideal. And the ideal that we constructed in these terms here is this guy like this. Okay. Now, the point is that if I truncate the ideal now, well, you get to this. And on the other hand, if you compute it directly, you get to this thing. So finally, you have this equals this. This is exactly what we wanted to prove. Well, this is tough. This is tough. Yeah. It's so what we did finally is well, the first, all the ideas are very natural, but put all together, this makes this thing very complicated. So there were how many? 4 ideas actually. Well, no, let's see. How many ideas? So first is linearizing from C to gluing all these spaces into an algebra, then truncating for your algebra to be a sister algebra, then taking the bicommutant. Why? Because of that nice lemma of the bicommutant. Whenever you see NV, if you know a bit of quantum group, you know that it's better to work with the commutant of NV. It's that lemma we did before. So it's 3 ideas. Now the fourth idea. So these are somehow straightforward. Okay, linearizing, truncating for sister algebra, taking the bicommutant. Now, once you get to this, you have to model something. And there was this idea of getting rid of U and star, just replacing the free algebra. That free algebra is modeled by tensors, very natural, modeling by tensors. And well, here in the proof, technically, you need somehow to take this dual somewhere, which is there for counterbalancing these commutant things that you took somehow. That's the idea. So there are 5 ideas in all this, but all standard. If you spend some time on it and think at it, it's standard. So maybe once again, well, I don't know if this look complicated to you. Should look at Malakarn's paper, which is 4 pages, but it's the same thing. I mean, it's but there it's assumed that all these things, many things are known here. Otherwise, you have Boronovich paper. So personally, I was that's what I did at the time when I started, like 25 years ago. Just spent a week in reading that, and I didn't even know that a square must be the identity. Well, it depends, but that's what we're doing here. A square is the identity. So yeah, it's even simpler with the square is the identity, because when it's not, this R operator becomes, instead of which produces somehow the unitarity and the duality, instead of I go tensor I, it can be an arbitrary vector with some kind of whatever young box or things there. It's more complicated. But so yeah, maybe that's a good reference. Yeah, Voronovich paper definitely. So what else? Maybe the book by Neshvev to set. Yeah, I think there Voronovich is explains. Also, maybe papers by Bichon. Yeah, Bichon should have something in. He started with doing these things like over somehow arbitrary fields, and there you don't have that many tricks as here. We comment all that, so have to be very careful and very more conceptual. So on this, you see, there are some computations here, and it doesn't really look like somehow really grotesque stuff. So if you want that, better go to Bichon and yeah, these guys. I mean, yeah, you need somehow more arbitrary fields, things like that. Here you have too many tricks and too much knowledge, okay? So that's why Sarah's paper is very short. This presentation was short too. We know too many things in overseas, so we're very tempted to use all kinds of tricks. Okay, so that's for the duality. So at least the statement is very simple, right? So no question about it. Now let's get into some applications. So there are enormously many applications. Why? Because we have a bijection. So all we've been talking about in the previous lectures, all that reconstruction, all that has reformulations in terms of categories. Can you forget about quantum group to categories once you know this? So it's as wide as quantum groups themselves and these tensor categories. So of course it's a bit different. You can do other things with them. So what to have an application? Well, let's go back to the things we're interested in, right? We have four main objects, un plus, un plus. I mean, especially un plus, right? Because these are the quantum groups that we introduced, and for the moment, don't know much about them. But we'll include in the discussion also the classical versions, which are not that trivial. They're actually more complicated than the free ones, but we'll see this later. So how to approach this? Well, it's just clear. I mean, UN plus is the biggest quantum group. So tensor category, of course, the smallest, right? It's not generated by R. So you have to understand this category generated by R. That's your formula of R. Now, well, someone must tell you this idea, you know, finding yourself. So I don't know who came with this thing, but well, it was math from the 80s, maybe the 70s, 80s, yeah. That R is a semicircle. So someone tells you this, it's a semicircle. So you have to get into diagrams and find somehow diagrammatic models for such guys. And if this is a semicircle, the category generated by it somehow must be some diagrams. So you have to get a bit into diagrams. And if you get into that, you reach to a conclusion that there are some quantum groups have the property that their Tannakian categories are somehow spanned by diagrams. And that's what we call easiness. So we reach to a theory called easiness. And as many examples, we have these four guys we're interested in. And once we develop the theory here, I will solve this problem. So that will be the concrete application, computing the law of the main character. So how to do that? Well, once you know the category, you just count the dimension of the home spaces. That's the moment of the measure, and you recapture the measure afterwards. Standard probability techniques. So it is very straightforward. I mean, just wouldn't just bother by UN plus Tannakian right away. It's the category generated by R. That someone must tell you that it's a semicircle. You have to look into diagram. You can do it without diagrams with spherical algebra. So yeah, diagrams. And then with these diagrams, you can do a lot of things. Okay, that's the idea. Now, I think I'll just tell you right away what happens here is best actually to, yeah, believe me, there is a kind of easiness condition going on there. So let me tell you what it is. So I take all the partitions between an upper core integer k. I mean, k is black, white, 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 black, etc. So put k like this, L like this, and just have partitions of these sets, having k plus L points, okay? Now, independent of the colors. Now, I take for any KL a subset of these partitions, not all of them, and I say that these form a category of partitions. That's the definition, category of partition, when it's a bit like for categories, it's double under the horizontal concatenation, that's about the tensor product, the vertical concatenation, and there things will, it has to match the black-white thing here and here, I mean the colors. Stable under upside down turning, with technically you have to invert the color when you do that. Now the identity, meaning the identity partition like this, must be in each PKK. And now the semicircle must be in it. So the white, black, and black, white semicircle must be in it. It's very similar to categories, and actually it's a delinearized version somehow of the simplest categories that can appear. So to be more precise, that's the thing. So quantum group is called easy when this Tannakian category is spanned by certain operators coming from partitions, and these operators are like this. So I take T1 n, the basis of Cn, I want to apply T pi to my tensor, and I sum some Dirac symbols and then everything here. So the whole point is in these Kronecker symbols, how to define them. So remember, pi is a partition between k points with colors and L points, okay? Yeah, let's not bother about colors for the moment. So k points here, L points here. Now I have a multi-index, U1k, so obviously I put it here on my points, J1, Jn here on the points. So in this situation, I have these two multi-indices connected by a partition, okay? So I just look at if it works or not somehow. So if any block of the partition has equal indices everywhere, my Kronecker is 1, otherwise it's 0. We have to think of this as, so first of all, of course, partitions are pictures, right? You put strings between things in the same block. So partition and picture, you have to think of it like something is happening there, okay? That's the whole idea of partition. So you see when, let's go back here, when composing vertical concatenation, that's the composition. You have to assume that something falls here and then becomes something else on the bottom. Some kind of particle, it's a kind of Feynman diagram. Well, let's not get into that, but something is happening, okay? That's the idea. And here too, something is happening. Whenever we put these indices, it can work. This one, it cannot work. It's 0. Okay, so that's the definition of easiness. So what does it mean? The quantum loop is easy when Tannakian category is the simplest possible thing. It's spanned by partitions. And this might look maybe a bit complicated at first sight, but there's nothing simpler than this. If you really want things to work, it won't work. Then that's the simplest possible thing. And now, as theorems, so our basic quantum groups are all easy, coming from the following categories. So for n is the usual pairings, n plus non-crossing pairings, un. So this was in the self-adjoint case. Now in UN you have to bother about the colors. So these are the so-called matching pairings. Matching meaning vertical strings can be white, white, black, black, and the other strings, those like this, it's only mixed, white and black. And NC2 here is the intersection. Okay, so it's matching or crossing pairings. Why is this true? Well, actually, the classical case is well known. These are the Brouwer theorems for n, un. It's exactly this Brouwer. Or if you're not sure why duality other things, but no, really Brouwer, yeah. That's these are called Brouwer algebras, this span of things here, this kind of guys. So that's Brouwer, definitely. But it also, if you look at Brouwer family, you need some kind of Tanaka there. So for some Tanaka. And on the right, for some Tanaka too, but the one that we proved here, the Tanaka for quantum groups. So why is this true? I was saying that UN plus corresponds to the biggest possible category, the smallest possible category generated by R. Well, there's the non-crossing pairings, right? What else can it be? And here, well, they must be white, black, and black, white, so they're matching. Now, I'm passing from UN plus to UN plus to UN plus. You basically forget the color somehow. That's what you get this. Actually, you can get Brouwer too from this, so from passing from this to this. Now, instead, the commutativity relation, a B is BA, and then B is BA is like a cross, we add crossings. So you get these things. So okay, all this follows from Tanaka. That's the idea from what we did, and the remark that in the classical case it's Brouwer for the results from the 40s, and this is like free Brouwer somehow. Very good. So this is the theory. Now let's do some applications. So first is that remember we have this operation free complexification, and in particular un plus contains the free complexification of un plus. Well, it's an isomorphism. So this is very nice and proposed by Tanaka because you see, I mean, these things, you have the categories here. You take the free complexification, that's something that we learned at the representation theory level. That's a very simple operation. So also at the Tannakian level, you can see what's going on there with colors and everything. You're somehow coloring. That what means the pairings. That's what means free complexification. So you get this right by coloring. So yeah, in this situation, we have an inclusion. Tannakian categories coincide, so isomorphism. So this is amazingly interesting because in a classical case, we already talk about that. So from pricing from n to n, you need to take the algebras, complexify, and then go back via exponentiation. So there's no other, there's no simple way from n to n. Here, it's just free complexification, so it's simpler than in a classical case. Now, also once you have this, so free complexification was meaning to multiply coordinates by a free unitary. Now, if you take the projective version, the unitary will cancel, so you get the same thing. So you get n plus is n plus. Of course, all this is modulo usual equivalence relation, right? Quantums are equal when their star algebras are equal of smooth functions. So well, this is amazing. I mean, in a classical case, these things have nothing to do, and you definitely have projective geometry and real and complex. And here is the same. So in the free case, there's only one geometry, projective. No? It's at the same time real and complex. So extremely deep philosophically, all this. Right? You can go far away into non-commutative geometry with this kind of ideas. Now, well, let's go to characters. Okay, that's the nicest part now. All this was algebra, somehow philosophy. Let's go into tough analysis very quickly. So we'll be back to all this in the next lectures. So let's compute the main characters for these quantum groups. And the point is that the moments are just a dimension of these home spaces, but which are now formed, spanned by partitions. That's easiness. The problem is that at n fixed, these partitions are not linearly independent, but if you work a bit with n goes to infinity, they become linearly independent. So finally, it's just a matter of counting partitions. And so here are the numbers on n. What we count here? Pairings. Well, number of points must be even, right? So that's why k is 12, otherwise it won't work. It will be 0 the moment. Where is 12? How do you count? Well, you have 12 minus 1 choices for the neighbor here, and then 12 minus 3, 12 minus 5, and so on. That's a so-called double factorial. Now, for n plus, you have to count non-crossing pairings, and here you get the Catalan number because, yeah, you do a recurrence. I mean, you see, you have your points, and then this. You just take the first semicircle. Since it's non-crossing, things here and here don't interact. So you have a recurrence, right? To solve that, you get Catalan. That was for orthogonal things. In the unitary case, well, now k becomes colored. So it's this kind of numbers, but a bit more complicated depending on colors. So yeah, now we can compute the characters. So we get these things from the moments. So what do you have? Double factorial, Catalan, and complex versions. So double factorial means real Gaussian, hope you all know. Well, this you have to know that it's Wigner's semicircular, the measure having Catalan as numbers. And here you obtain the measures which are complexification, so complex Gaussian, of course. And here we equals circular. So, well, how to prove this? The problem, this is quite tricky. So you have the moments. Let's just talk about the real case of a complex, the same but more technical. So in the real case, I give you these numbers. 12 factorial, let's say, what's the measure having these moments? So the even moments, the odd moments are 0, okay? Okay, must be even. So problem, what's the measure having odd moments 0 and even moment double factorials? And well, if you know that it's the Gaussian law, well, if you know, you're done. But if you somehow remember there's the Gaussian law, you just compute the moments of the Gaussian law, right? The partial integration, whatever, you get to these factorials and you're done. Okay, that's your proof. The problem now in the third case. So the first case is that perfectly known. The second case you vaguely remember, and this is by partial integration. But the third situation is when you don't know the answer. So what's the measure? And you have to reconstruct it, and that's the so-called Stieltjes inversion. So there's a method in probability. Once you have a series of numbers, you can compute the measure having these moments as numbers, but it's a bit technical, involving some complex analysis. The idea is you arrange these moments into a series and then you do some complex analysis manipulations, and finally it's in complex on the real line, you recapture your density. So there's a method for that, but once again, it's a matter of knowledge. You have 3 levels. You perfectly know, you kind of know, and you do some calculus, or you don't know, you do Stieltjes inversion. So that was here for Catalan. Yeah, depends on your knowledge. That was together you do Stieltjes inversion. And here, well, it's a kind of complexification. So yes, we'll talk a bit more about this later in some other lectures. So conclusion now, we have, what do we have? The theory of easy quantum groups has many applications of Tannakian duality, very simple axioms. So the category must come from partitions. These guys has many examples. Now, connections with probability, free probability, definitely. Random matrices, and Wigner is a random matrix guy, Nobel Prize in physics. Voiculescu, you all know him. So very interesting things going on here. And then many other potential examples, because I remind you, well, this comes from pairings, but in the definition of easiness, we have partitions. It works for any partition. So there are many, for instance, the category of partitions themselves or non-crossing can give us some other quantum groups. And well, I'll tell you the answer in advance. P comes from the symmetry group, and then C comes from the quantum permutation group. So once you see this, yeah, there's the next thing to be done to understand permutations, quantum permutations, and then large easiness, and then go to probability and things like that. So that will be the next plan for next time. Okay, guys. So I hope that you like it. Yeah, that's retiring Tanaka, but as I told you, there are many references there, and you have to look at somehow all of them. And yeah, anyway, we'll end up learning anything. So once again, Saavedra for the story, Duplicate Roberts, Delini, Voronovich, book by Neshvev, two sets, Malakarn, and then a paper, and planar algebras too, if you want, by Von Jones. Yeah, many things. Okay, so see you next time for quantum permutations. That's gonna be very interesting, I guess. Bye bye.